Hello guys, we are the Capital Rocket team. We are going to present the extravehicular activity, AVA, the Bluebird. I am Hannah.
I'm Victor. And okay, so without further ado, let's start the project. First, we're gonna present a quote from the famous scientist Neil deGrasse Tyson. He says, "Space exploration is a force of nature unto itself that no other force in society can rival. Not only does that get people interested in sciences and all the related fields, but it transforms the culture into one that values science and technology. And that's the culture that innovates." And this is a really powerful conclusion that we get to witness every day in the academic environment, where many students are getting involved and interested because of the recent innovations in the field. And that was the inspiration for our work. So for the first part, we're going to present what is a spacesuit. And a spacesuit is a really complex system that is commonly comprised of as much as 16 systems, as is illustrated in this picture. So as you can see, there are many parts, and each of these parts can be further divided into many others. So it's really complex and constitutes a lot of parts. And one thing we realized doing this work is that this system really needs to be reliable and robust to failure, because there's high stakes involved where any failure could lead to catastrophic events, and that's really hard to design. Mainly for this reason, we decided to focus on some subsystems without detailing all of them, and our work will be divided on these four main sections. First, we're going to describe the microspacecraft, where we're gonna detail some of the engineering parameters and the suit specifications, and we're talking about things like thermal insulation and the PLS system. And then we move to the space medicine, which we gave a lot of focus. That is the part we detail how we're going to monitor the health of the astronaut, and we're going to talk about the biological signals we're going to capture and how we're going to process it. And for the next part, we're going to talk a little about how we're going to monitor the suit itself. So like mainly, you're going to talk about the temperature sensoring, the pressure, and the radiation sensoring, for both the external and the internal environments on the suit, which are very important. And in the final part, we're going to take all the subsystems we described, and we're going to talk about how we're going to integrate them and how they're going to be constituted to form the suit as a whole. So for the first part, we're going to talk about the microspacecraft.
So as a microspacecraft, the main aspects which we're analyzing are the heat transfer of the body, the body and the regulator seal, the portable life support subsystem, and the gloves, and also the communication system. First of all, in order to catch the temperature between 23 to 27 Celsius degrees by controlling the in and out heat flow in the suit, we had to choose a really efficient thermal insulation, which was 7 layers of polyester film. And right now, I'm gonna just say that we're gonna jump a little bit to the other layers, and furtherly, we're gonna talk about the electronic layers and the internal garment. And the water seal is basically a nanotechnology fabric which has the gaps between the fabric. They are so small that they prevent from water absorption. So they are in the order of micrometers. Like you see in the image, we've chosen a 50 micrometers one, and actually want to prevent from protecting our electronic devices in the suit. The last layer is going to be a regolith to protect from regolith, and I'm going to use an ortho fabric, which is a really endurable one and really resistant. And what we're going to do, we're going to underweave an electrostatic system in this fabric to apply a direct current in the suit, and then actually it can avoid from fixing from the regolith particles, because when the sun irradiates its radiation, the particles, they get ionized and then it can get sticky in the suit. So to complete this suit, we're going to use also a magnetic device to clean up the suit. So it actually is going to be an attachable device. So it has like a multiple magnetic roller and the sleeve that actually clean it up like thoroughly, and the astronaut can come back safely. To the glove, we have 3 layers to the glove. The first one is the cotton layer, so we can actually a little comfortable. The second one will be a natural rubber glove to make easier the movements of the hand, and the third one is going to be changed soccer goalkeeper glove, so with some accelerometers on the tip of the fingers, so when the fingers do a movement, it actually sense the movement and makes and transform it into voltage, and actually the screen can sense it and the touch of the astronaut. The portable life support subsystem, or PLSS, actually contains 2 oxygen tanks, actually 2 ones, so then we can actually maintain the oxygen supply whenever happens a pressure drop on the suit. And the CO2 scrubbers, they actually clean up the internal atmosphere, because they clean up because the astronaut is every time breathing in O2 and breathing out CO2, and we actually gonna clean up this atmosphere so it's actually breathable. The fans, they are used to maintain the flow of this air in the atmosphere. So for the umbilical cord, we're comparing the umbilical cord from scuba divers, and we're gonna use the umbilical cord while subaquatic missions. So it's gonna supply energy, oxygen, and cooler liquid for the astronaut. Here we can see a scratch from the backpack. Over there we can see the cartridge, the contamination control cartridge, which could be the CO2 scrubbers. And down there we can see the O2 tanks. They're going to provide this oxygen for the astronaut. The last part we're going to talk about is the communication system, because we are actually trying to use the 3G system, and they actually allow, because they already know protocols, they allow us to use voice calls, video calls, and low frequency data. It's actually our main requirement. And actually that's it for the micro spacecraft. And right now we're going to talk about the space medicine.
Okay, so for the space medicine part, what we're going to do is detail what are our requirements for choosing the sensor, and we're going to explain a little bit about the reasoning we made to choose each individual sensor or algorithm to process and give this vital information. So for the first part, we're going to talk about the body temperature. It's a really basic measurement, and therefore it's quite commonly available as products, and it's very accurate and economic already. Like, this is one of the first 2 requirements. But one of the main things, one of the main challenges in deciding the sensor is actually deciding where to place it, because there are a lot of parts of the body you can place the sensor, but you get a lot of variation in temperature from each of these parts. So after deciding this sensor we're going to use, which is the SCORTEMP CM210 by Terumo, which is a very well-established commercial sensor, we looked for researchers to base our decision for the spot to place it. And we found a research that showed that placing it on the celiac plexus, which is illustrated in this picture, can give a very accurate and meaningful measurements, mainly because in this spot you have a lot of vital organs. And when you have motion and a lot of activities, the blood tends to go to these organs, and these increase the temperature and can give information about the motion and how the temperature is distributed in his vital organs. So that's our decision for the body temperature. For the next part, we have the electrocardiogram, which is a very important measurement that can give us a lot of information. And what we're looking for here is a quality signal with mostly an ergonomic arrangement, because it can't be discomfortable for the astronaut, because he's going to be wearing it for long periods of time. And one of the requirements is the most difficult one is for it to be practical, because most of the ECG electrodes uses gel electrodes, which needs to be constantly replaced, and that increases a lot of time for the preparation before putting on the suit, which is really hard considering space missions. So what we were looking for here was to use dry electrodes, which doesn't need to be replaced, and can give a lot of arrangement illustrated in the picture, where you have a lot of sharp edges to collect the signal. And what the study shows is that this arrangement is really good to filter this motion noise commonly because of friction and movement on the the only downside here is that it isn't yet a commercially available product, so it's going to need further development and testing to be actually used. But as innovation, this is actually a really good proposition. So for the next part, we have the electroencephalogram, and the requirements are similar, and you actually need the quality signal to be ergonomic, and this ergonomic part is quite important because the head is a very sensitive area, and it's really hard for you to place all the electrodes one on one. Every time you're going to wear the suit, it's really hard and it takes a lot of time. So we found this 32-channel quick cap that is shown in the picture. There is also already a helmet which connects all the 32 channels in a very comfortable arrangement that can facilitate the vestment. And this uses semi-dry electrodes, and semi-dry electrodes, apart from the dry electrodes, they actually have a moist on it to facilitate the transfer of the signal. But this moist doesn't actually need to be constantly changed. So you can have it work for long periods of time with the same initial moist. So this makes it easier to put on. Okay, for this part, we have the blood oximetry, which is a really important measure that we are going to use to extract a lot of useful information. So here, the workings of the blood oximetry we're going to use consists of two LEDs. One that emits in the red spectrum and the other in the infrared. And a receiver. What this does is it relates the amount of radiation reflected to the photodiode that's shown in the picture with the blood volume, specifically the arterial blood volume. And one of the main challenges here is that you get a lot of interference from light reflected on the skin and on venous, from the venous blood. So it's kind of hard to separate these components. So for this reason, we found an article that do a great job of conditioning this circuit. And we actually designed the circuit and made some simulations to test it. So what we did was we first got a typical signal from a database, from the PhysioNet database, which is its first graph. And this signal is already treated, so it already has good quality. So what we did to test the conditioning circuit was we added some noise to it, specifically some white Gaussian noise, and we used this signal, this noise signal, to pass it through the simulator using Spice and checking out what the result would be like using the circuit we designed. And this third graph shows what the result is like. And as you can see, it's quite similar to the first one, which was already treated with a little delay, which is not relevant in this case. And this can show the accuracy and the quality of our conditioning circuit. And finally, what we have after extracting all these raw biological signals, what we're going to do is to actually process it. So in this picture, we have examples of PPG, ECG, and EEG signals, typical ones that we're going to use to extract different informations. For instance, first, we're going to extract the blood saturation from the PPG, which is quite a common method, where you can relate the blood volume to the saturation by empirically drawing a curve and testing the algorithm. And actually, the whole system we used for this part was based on a recent research from from the University of Texas, and they actually made a whole system, a whole algorithm that can extract both the blood saturation, the respiratory rate, and the cardiac frequency. And the workings of the algorithm are quite complex. They use a lot of transforms and analyze a lot of the parts, the peaks and the values on the PPG signal. It's more detailed in the report, so we're not going to talk deeply about it. But one of the main things we propose that is really important considering the application is the blood pressure, because mainly on hospitals, what you have is those wrist cuff sensors that they use to estimate the pressure, but that's not very good considering the application. You can't have it. It takes a lot of space. It's not very accurate, and it needs motion to compress and decompress the air. So it's not very practical for our application. So what we proposed, and based on an article that's actually being developed in the university, is we proposed blood saturation using PPG and ECG signals, where you can relate those two to extract a blood pressure measurement. And there have been recent developments in this area, a lot of great research to validate this method. And that's a very interesting innovation that it's gonna become available for the spacesuit environments. It's actually already being used in some cases. And finally, the drowsiness level. The drowsiness level actually relates to how tired the astronaut is, and this is also very important to monitor how it's doing and its health. And this is going to be extracted using the EEG, which is a very common method, and we describe it in the work more thoroughly. For the next part, we're going to talk a little about the system's health. Now, we first talk about how we're going to extract the biological signals and process it. Now we're going to talk about how we're going to monitor the suit itself, the conditions, the environmental conditions residing in the suit itself. Mainly, we're going to talk about the temperature, pressure, and radiation. And for these cases, we have to capture both the internal and external conditions. Internal to the suit and external on the environment, the atmosphere. So for all the cases, we're able to find sensors that could work in both situations. So each sensor here is going to be used for both cases, only changing the placement. So for the temperature, what we're looking for is a sensor that can adequately measure the temperature range expected in the Martian surface. So it's estimated to be around 100 Kelvin to 350 Kelvin. And what we use here is a commercially available, which is called Type T thermocouple from Omega. And it uses infrared technology to estimate the temperature. And its measurement range is actually more than we need. It's 13 Kelvin to about 663 Kelvin, which gives us a lot of space to measure, and we wouldn't have to worry about it. So for the next part, we have the internal and external pressure sensors. And here, one of the challenges is to make it immune to electromagnetic radiation, which is quite common in the atmosphere of Mars. And also, you need to have a compact size one, so it's easier to place, and we can distribute with more thoroughly to the body. And the one we found uses optical fiber technology, as they're depicted in this picture. So the workings of the sensor is basically it emits a signal from one end of the sensor, and it receives in the other, and you analyze the power loss from the transmitted to the received channel, and you can relate that to the pressure being applied on the sensor surface. So this is a really recent study from 2018, 2017, and it's a really great innovation to be applied to the EVA too. So next, we'll talk about the internal external radiation, which is quite dangerous and needs to be measured. And for this, we limited the spectrum of the radiation we're going to analyze to the ionizing radiation type, because this is the most dangerous. And specifically, we're going to focus on neutrons, high energy particles, gamma rays, and X-rays, which are the most challenging one and can do the most harm to the astronaut. Our system consists of a scintillator crystal, which is sensible to this spectrum of radiation. And the response of these crystals can be detected by a photodetector. And you can relate the measure being taken in the photodetector to the amount of radiation incident on the crystal surface. And that's how we're going to measure it. Okay, so for the next part, we're going to talk more about how we integrate all these parts that we proposed on what would be a normal suit with all these main parts we described in the introduction section. So
to achieve a desired proper usage of the system, it is actually necessary to take in consideration the subsystem assembly. Let's first talk about the layers. The suit's formed by 10 layers of fabric. The first one is internal garment, which will contain the system health electronics, and the second layer, layer will be the layer with electronic devices, other electronic devices to make other measurements. And have the thermal insulator, and the last one will be the waterproof layer, and then the regulated CO layer. And aside from the internal garment and the layers, there's also the PLS. How we're going to connect them? There's going to be a tube allowing the flow of air and the cables between the electronic systems that will be in the PL cells, either external and internal electronic devices.
Yeah, like Brendan said, we're gonna have a lot of sensors on the backpack, the external sensors, and the battery, and all these electrical cables are gonna pass through this tube and gonna arrive on the main part of the suit. What they have to reach is the processor, which is placed on the wrist, right next to the display, as you can see in the picture. This is a design we made with Illustrated to give a general idea of what our proposition is. And one of the main challenges here is that we can pass the cables through the tube and to the external part of the suit, but the internal sensors, actually the space medicine sensors, they really need to be tightly fit to the body, because you can't really afford a lot of motion that would make a lot of noisy measurements, and really need a tight cloth. So in this tight cloth it's harder for it to be a part of the suit integrated directly. So what we did we designed a separate part. That is this left part of the design of the drawing, and here we give a general idea of where the placement of the sensors will be, the pulse oximetry, the electrodes, and the body temperature. Here we aren't counting for redundancies, which we are expecting given the complexity and the necessity of the measurements. So especially the PPG signal, which gives a lot of later measurements after the processing, we really need it to be redundant and robust to failures. So the way you're going to connect this internal garment that is related to the protocol for the astronaut to wear the suit is he's first gonna wear this internal garment titled fitted, and then in this internal garment we're gonna have a cable sticking out his neck, joining all the connections. And one thing we did here is for each sensor we designed a module of its own that is comprised in all the cases of three main parts. That is an ADC converter, a memory, and a voltage regulator for the first to be able to use a higher voltage battery to avoid power losses. So the necessity for the ADC right next to the sensor is because if we pass long cables through the internal garment to the processor, this can causes a lot of power loss, and this would then harm the quality of the measurement. So what we did is we digitalized these measurements right after the acquisition, and we start in memory instead of directly feeding the processor with this information. That's useful because in this way, the processor can establish a communication protocol. Mainly, we decided for HUC where it can request for information and get it back whenever needed, not all the time. And finally, all this information is stored and in each module and acquired by the processor will be transmitted with the 3D communication system that is really for handling high frequency measurements such as the EEG and the ECG, and will help us integrate all these parts and communicate and give this feedback to the display and to the base where they can take the right actions to deal with any problem that may come.
So we can see that the complexity, we can understand actually the complexity of building an aerospace suit, and actually we can see that it was really important to do these biological researches, and it's actually really important not only to Mars, but as for the whole space research as one.
Right, and one thing to focus here is you have a lot of things well established for the parts, such as the helmets and the boots and the suit as a whole, the high torso and the sports. We didn't abort these issues mainly because we weren't considering innovating on them. So we mainly focused on the parts we thought could contribute to new innovations and experiments that could be used on the suit.
Yeah.
And overall, I'd like to thanks our professor Cristiano. He helped us a lot in developing this work. The Capital Rockets team, of course, the part of, and all the COBRUF staff for the support and organization. We really enjoyed it.
Thank you so much.
Thank you.
What will be the effect of Mars dust and radiation in your design and operation?
Oh, the dust. The gamma radiation with the dust. Yes. The dust. It can actually contaminate our location from where the astronaut is at. So it's actually really dangerous for the health of the astronaut because it's really.
And about the radiation, typically the suit is able to filter most of the radiation, but in case of a leakage, our sensors will be able to detect it and give feedback to the astronaut for him to be able to come back or go to safety before some harm is done.
Thank you very much.
Thank you very much.
Hello, can you hear me? First, I'd like to congratulate on was very interesting. And I would like to make some questions about and comments about biomedical sensors. We'll start with the temperature measurement. First of all, I thought that measuring this core temperature instead of the skin temperature is a very good idea. And the second comment, you put that on your work and now on your explanation, that you are going to put the sensor in the plexus celiacus. Actually, this structure, the plexus celiacus, is an internal structure. So you just can reach that with a laparoscopy. So just open the belly and put that inside. So what would you like to say it's put on the epigastrium, that is the skin region that corresponds to that region. Perhaps I read the paper that you cite, the Huang 2017, and they do write there plexus, solar plexus, but this comes from the Chinese medicine, like chakras and etc. And that's a nerve plexus just inside the belly. So you just could put epigastrium. It's okay. So just a conceptual thing. Then a question that I have is that you said that you are going to use the sensor CM210 by Terumo, but what the Huang said there is they developed a different sensor, just because the CM210 it's a big sensor, and they had to have a big heating exchange, and then it's big and just can be used inside a hospital, or you have a big source power to use them. And they validated that inside surgeries, so the measurement is very accurate in reference to internal temperature. But that's not the sensor that Huang uses. He uses that second sensor by Yakamaji and Tamiki. They work from 2003, and they differ in measurements of thermometry. So the first one, the proposed method by Huang, it's called dual heat flux method, that was proposed by Kitamura in 2010. And the model CM210 uses the principle of zero heat fluxes method. So there are two different methods. And so I was wondering how you are going to use Huang's method with the sensor of Terumo. So I didn't quite get it. So could you explain for me? I think I can hear you. Just a moment. Could you speak again? I can't hear you. Are you mute? Mute? Now I can.
Yeah. Okay. Right. So okay, for this part, yeah, right. And on the article, they use the data to validate the sensor, and actually the core temp to validate, and the other one they developed. So in this case, we like to cite that they work, mostly because of the contribution of the placement and all. But we decided to use the commercial one in this case because they used it in the paper, so it's actually a good one to give an accurate measurement. And because temperature is actually a well-established measurement that doesn't actually need doesn't actually give a lot of problems typically, we decided to use the one they use it as validation instead of the one they proposed. It's mainly because of it, for this reason actually.
Yeah, and the development of the suit will be really easier and if you choose that.
Yeah, that's right.
Yeah, and a question was about the paper itself. They say that the most common to measure the head in the front of the part, and this is the equivalent to measure on the epigastrium, so on the plexus. But this is not quite true, because on the forehead you have not just brain and bone and skin, as you have on the plexus. You have a very thick layer of air that we call frontal sinus. That you have sinusitis from there, for instance. And air is thermal isolator, so probably it's not the same thing, because on the belly you don't have this thick layer of air. But anyhow, it's not about you. I think that just on that paper they should pay attention on that, because there are two different places actually, in terms of getting temperature. Just going now for the ECG, the electrocardiogram. You described very well the electrode, but not much about. I saw on the suit that you had just one spot for the electrode. So how many electrodes are you going to use, or how the derivations? Do you have any idea, or what kind of measurements you're going to get from them?
So what we were expecting, and I don't know if it's well detailed on the work, but we're expecting actually 3 spots for the ECG sensors we talked a little about redundancy and the necessity for more measurements, but we decided not to give those accurate numbers and show them. What we did mostly was show the location and how we integrated that with the other sensors, and to add one more to this grade would be easier. We'd prefer to give more focus to the algorithm to process this information there.
Perfect. And I think that's another comment about the electroencephalogram. And you use that quick cap with 32 channels to acquire the EEG. But then you just use that information to detect drowsiness afterwards, right? So actually, on the same website that you get the commercial cap from the quick cap, I don't know if you've seen, they have a video of a guy controlling a drone. Have you seen that? With the cap. And they have even a paper on that. And that could be something interesting to integrate. I mean, of course, you have to think about the accuracy of that. So normally it's around controlling brain-machine interfaces. You can get from 50 to 60% accuracy. So perhaps something that you can go into detail in the future. Because as soon as you have such a rich sensor, like getting 32 channels, you could get more of that just measuring drowsiness. Because to measure drowsiness, you just have to have 2 electrodes on the occipital, for instance, and that's okay. So you don't have to have a huge cap to get just drowsiness. So you can control drones, rovers, open the communication systems, but this requires further processing of the signal. So you have to build consistent algorithms, how to send them to the base, where it's going to be processed, how you're going to feedback. The astronaut has to be trained for that. So it's not a simple task, but it's also an innovation thing that should be thought about. And also about detecting epileptic seizures. So there are some initiatives that measuring stochastic wave analysis from the EEG. You can predict with even 25 minutes ahead crisis. So you could warn the astronaut or take measures for them to be warned about that. And with such a nice cap, you could get that from your measurements. About the oximetry. Congratulations on the simulation on the circuit. I thought that was very nice. And I think that you said about the sensor location that would not fit on the finger. Actually, I thought that in the glove it could be integrated without any problems. Like it wouldn't actually. Or even in the ear, you have to have the ear caps for communication. It could be integrated then there with no problems. Or even on the toe, on the feet. So why not there too? So you could go for simple solutions that the risk is not very common. but you actually presented a very nice simulation and clarification of how you could get that signal. And the last thing I would like to comment is that I thought very nice and inventive the solution of measuring the blood pressure with the technique that you used. And I think that were my comments. I would like to congratulate you from your job. I thought it was very nice.
I have another question. I would like to know, in your opinion, how spacesuit and microgravity studies could improve Earth's medicine, the best way we can focus these studies, this effort right now.
What do you actually mean by improving?
I would like to know, in your opinion, which technologies and which studies should we focus right now on microgravity and spacesuit technology that can be also used as dual technologies and dual studies on the medicine, on treatment, disease detection, even brain-machine interface, exoskeleton, and so go.
So, for instance, using the radiation system, the crystals we can actually use, and we can actually do the study from, for instance, we can actually bring up some cancers to the spacesuit and to the environment Mars, and we can actually see the growth of cancers and how the cancer they act on radiation and space radiation. We can actually bring it up to our reality and give a different treatment to the cancer using this kind of data on radiation.
And also relating to microgravity and designing sensors to capture these healthy signals. If you consider a microgravity a different scenario, you can actually design sensors and research for sensors that are more generous for a lot of different applications. And we can extract a lot of good measurements from the astronauts, because they are being constantly monitored. So all this information we're communicating can be stored and further analyzed to study a lot of different medical status and signals.
Thank you.
Hello team, congratulations on your work. It is a good work. And I before I finish, I'd like to know if you want to tell us a few words before I finish.
Finally, talking a little bit about this experience doing it, we found out that there are a lot of great challenges that can be approached in this field. You can relate a lot of different areas, and it's not the work that someone from a single area can do. You need to really integrate a lot of different people from different fields, and that's the only way you can have a good work, because it really involves a lot of things, and it's really complete in this manner. And also about the integration, we found out that it's really hard to integrate all this reliably, and to think about all the possible consequences that could happen in the outer space. It's a really great exercise to try to imagine it and try to solve all these problems that it's.
And it was actually a main problem because it was actually really interesting doing this job, this work, because it involves all areas of engineering. So because we actually study aerospace engineering, most of us, and some of us study also electronic engineering, and we actually to use it as resources for our project. So it was really, really interesting to combine those, not only our aerospace, but also electronic, and make it as one. So working with that was really resourceful for us and really entertaining as well. So doing this work, and we actually had a really good job doing the work, and I think like it improved our lives for sure.
That's true.
Thank you very much.
Thank you very much.
You know that our working at this project has been useful for you personal and professionally. So it is really great. Thank you very much